After analyzing the Thomas-Fermi model for the atom and considering the results that we are getting for this system, we can say several things. For example, that although the general trends are quite right, there are some problems with this model we're going to describe below here. First, there is no bonded solution for negative atoms within this Thomas-Fermi approximation, although we know that this is the case in reality. Then the asymptotic behavior is grown. For example, the induced electronic density close to the nuclei diverges, although we know that in reality it doesn't diverge. Very far from the nuclei, it's going to zero within the Thomas-Fermi model as R2 minus 6, although in reality it decays exponentially. Then the energy we have for the Thomas-Fermi atom is too low compared to real atoms. Calculating and analyzing the induced electronic density in the Thomas-Fermi atom, we see that there is no shell structure, although in reality in the atoms we can see that some shell structure associated to the bands that are getting occupied. Then within the Thomas-Fermi approximation there is no chemical bond binding, which basically means that if you had two nuclei close each other and calculate the energy on one hand within the Thomas-Fermi model, and then you calculate the energy when you make the two nuclei very far from each other, the energy in this second case is lower than the energy you have when the nuclei are close each other. So basically means that they don't want to be close each other, they want to be far apart each other. So that means that there is no chemical binding. So in order to overcome that, these difficulties, these problems, several improvements were proposed. For example, Dirac proposed to add another term in the expansion of the energy in terms of the induced electronic density. He proposed to include a term associated to the exchange, to the electronic exchange. Then on the other hand, as in the expansion for the energy, we consider the kinetic energy, which was associated to the uniform electron gas approximation, which in principle is correct when you have a constant electronic density. But here in the Thomas-Fermi model, the induced electronic density is not constant. So von Weizsäcker proposed to include another term, which was a gradient correction to the induced electronic density. This kind of improvements, actually they were able to solve some of the problems that we're analyzing here, but not all. So as remember that model was proposed as at the same time where Schrödinger equation was being developed. So some questions remained open somehow with this Thomas-Fermi model. The key question that remained open was the following. Was that strategy of considering the induced electronic density as a key ingredient to solve the problem a good strategy? Because that was like the strategy for density functional theory, as considering the key ingredient to solve the problem being, instead of the wave function, for example, the induced electronic density. But is it correct? And on the other hand, even though it's correct, could we be able to get any much better, any right, any correct expansion for total energy in terms of the induced electronic density, so that the results you are getting from that expansion are getting very reliable solutions? So that were the kind of questions that remained open to be clarified in the following years.